right, class, today I'm going to talk about Chapter 6, which is about rational expressions and functions. This chapter is going to require us to use a lot of the factoring rules we learned in Chapter 5. So if you're not feeling super confident about factoring, please make sure you go back and review. So our first section is about rational functions. A rational function is defined by a quotient, remember that means division, of polynomials and has the form f of x equals p of x over q of x, where our denominator cannot equal 0. Remember, we can't divide by 0, okay? What does this mean? This means we're taking a function, something like a line, right? The graph of a line is a function, so I could have a function x, and I'm writing that over another function, perhaps another line, like 2x minus 4. And the domain of this rational function is all real numbers except those that make q of x equal to 0, okay? So how am I going to determine what values are not in my domain? I'm going to do that by setting my denominator equal to 0 and solving for those values that would be excluded from my domain. So, first thing I need to do is factor the denominator if needed. 3x plus 2 is fully factored. Then I need to set the denominator equal to 0 and solve for the points not included in the domain, okay? And I'm going to write this in set or interval notation when I'm done. So I'm going to go ahead and I'm going to take 3x plus 2 equals 0. And now I just solve for x. I subtract 2 from both sides, so I get 3x equals negative 2. I divide both sides by 3. So I have x equals negative 2/3. So x equals negative 2/3. If I was to plug this in to my function, that would make my denominator equal to 0. So this is a value I need to exclude from my domain. There are two ways to write this. We can write this in set notation or interval notation. Interval notation is when we were working with a number line, right? So in set notation, it would be x such that, that's what this vertical line means, such that x does not equal negative 2/3. If I was going to write it in interval notation, you could imagine a number line, right? Here's our x-axis, this is our number line, but there's going to be a hole in our number line at negative 2/3. So I have all of this and all of these points, right? These are my domain except negative 2/3. So I could write this in interval notation. It goes from negative infinity to negative 2/3. And I'm going to union that, right? I've got a hole at negative 2/3, so negative 2/3 is not included in my domain. From negative 2/3 to infinity. So there it is in set or interval notation. You can choose your pick. Now for this next function, we're going to go ahead and factor the denominator. So I have x squared minus x minus 6. Okay, this is a trinomial. So I need to find the factors of AC, which is negative 6, that add up to B, which is negative 1. So some factors of negative 6 that add up to negative 1 could be negative 3 and 2. Now my leading coefficient is a 1, so I already know I can factor this denominator as x plus 2 times x minus 3. So step 1, factor the denominator. Check. Next, I need to set the denominator equal to 0 and solve. So I have x plus 2, x minus 3 equals 0. Well, we need to use the zero factor property here. So I'm going to take x plus 2 equals 0 and x minus 3 equals 0. And we learned this in section 5.5, that if I have two factors equal to 0, either one of them has to be 0 or both of them have to be 0. So this leaves me with x equals negative 2 and x equals positive 3. So in set notation, I would write x such that x doesn't equal negative 2, comma 3. Or I could write this in interval notation, imagining my number line. It goes from negative infinity to negative 2. Union with, it goes from negative 2 to 3, but there's a jump at negative 2, right? Negative 2 is not included. There's also a jump at 3. So that goes from 3 to infinity, okay? So when I'm given a rational function, I need to determine what our domain is, right? These are our new domains. Now let's take a look at this. I have 7x minus 14 divided by 3. And I want to know what's the domain. Well, I can't go ahead and set 3 equal to 0, right? 3 doesn't equal 0. For this function, the denominator will never equal 0. So that means there's no values I need to exclude. So my domain is going to be all real numbers or from negative infinity to positive infinity. Another special case is if I have 2x squared plus 1, okay? This denominator will never equal 0 because x squared is always going to be positive, right? So even if x was 0, I would still have 1. If x was a negative number, I would have I would square it to get a positive, multiply it by 2 and add 1. So this domain is also all real numbers. Now, just like fractions, rational functions must be simplified. If I have the fraction 2/6, we can simplify that down to 1/3 because both 2 and 6 share a factor of 2. The same is true for rational functions. What we need to do is factor the numerator and the denominator, find the greatest common factor, and divide those out. So let's go ahead. I have x squared minus 3x minus 18. So I need to find the factors of AC, which in this case is negative 18, that add up to b, which is negative 3. So the factors of negative 18 that add up to negative 3, that's going to be negative 6 times 3. Negative 6 times 3 is negative 18, and negative 6 plus 3 is negative 3. Now my leading coefficient is a 1, so I can use our rule that I can rewrite this as x minus 6 times x plus 3 based on these factors over here. And you can always check your answer by foiling. Now I need to go ahead and factor this denominator. We'll do that on this side. So I need the factors of 12. So AC in this case is 12. I need the factors of 12 that add up to 7. So 12 factors into a 1 and a 12. 2 times 6, 3 times 4. Oop, I think we have a winner. Because 3 times 4 is 12, and 3 plus 4 is 7. So using our rule, when I have a leading coefficient of 1, I can rewrite this as x plus 3 times x plus 4. Now, let's see what factors they have in common. My numerator has an x plus 3, and my denominator has an x plus 3. Just as over here we had a factor of 2, right? I could have rewritten this denominator as 3 times 2, and my 2's would have canceled. Now this x plus 3 is going to cancel. So I'm left with x minus 6 over x plus 4. Now this rational function is fully simplified. Let's take a look at another example. I have 3x squared minus 7x plus 2 divided by x squared plus 2x minus 8. So for our numerator, we'll do the numerator on this side. I need to find the factors of AC, which is 6, that add up to B, which is negative 7. So I think I know that I'm going to have to look at two negative numbers that add up to negative 7. So I'm going to take negative 6 times negative 1. Now, our leading coefficient over here is not a 1, so we can't use our shortcut rule. I now have to rewrite my middle term as a negative 6x minus 1x and factor by grouping. So I have 3x squared minus 6x minus x, so a 1x, plus 2. And now we factor by grouping. So what is the greatest common factor of 3x squared and negative 6x? That's going to be a 3x times x minus 2. Then I have a negative x plus 2. What's the greatest common factor there? Well, it's going to be 1, but I've got a leading negative. Do I like leading negatives? No. So we're going to write that as negative. We're going to pull out a factor of negative 1. Now I collect my greatest common factors. 3x minus 1 times x plus 2. Awesome. This is our new numerator. Next, I need to factor my denominator. Okay? I have x squared plus 2x minus 8. So I need to find the factors of AC, which is negative 8, that add up to B, which is 2. So 8, I could write that as negative 2 times 4, and negative 2 plus 4 is a positive 2. So I know I can rewrite my denominator as x minus 2 times x plus 4. Remembering I can do that because my leading coefficient A was equal to 1. So now we have our new function. So I have 3x minus 1 times x plus 2 over x minus 2 times x plus 4. Now, does this numerator and denominator have anything in common? No, I've got an x plus 2 and an x minus 2. It's important to remember that those are not the same, okay? So this is fully factored now and fully simplified. So we're done. Next, I'm going to need to factor this numerator and this denominator by grouping. So let's factor my numerator over here and my denominator over here. That's supposed to be a D. So I have AM minus BM plus AN minus BN. We're going to factor by grouping. The greatest common factor of AM and BM is M, leaving me with a factor of A minus B. The greatest common factor of AN and BN is going to be a N, leaving with a factor of A minus B. So I collect our greatest common factors. That's going to be M plus N times A minus B. Now I need to factor my denominator. I'm going to factor by grouping. So I have AM plus BM plus AN plus BN. Let's go ahead and factor by grouping. The greatest common factor of AM and BM is going to be an M. In this case, I'm left with an A plus B. And the greatest common factor of AN and BN is going to be an N. So N times A plus B. I collect my greatest common factors. I have M plus N times A plus B. So now I can rewrite this function now that I've factored it. I can rewrite this as M plus N times A minus B over our denominator, M plus N times A plus B. Now we cancel out their common terms. Both have an M plus N. So those cancel out. And my final fully simplified rational function is A minus B over A plus B. And these are different terms as we discussed in the previous slide. So this is fully factored. Now let's take a look right here. I have A minus 10 over 10 minus A. I'm going to rewrite that because typically we like to have the variable first, okay? That leaves me with A minus 10 minus A plus 10, okay? What do we notice about our numerator and denominator? They're different except for their signs. So I'm going to go ahead and take my denominator and pull out a factor of negative 1. That's going to be with negative 1 times A minus 10. Well, now I have some factors that cancel out. Okay, so A minus 10 divided by A minus 10, that gives us 1. So I have 1 divided by negative 1, which gives us a negative 1. All right, let's factor one more. I have P minus 2 over 4 minus P squared. Oof, oof. Remember, we like to have our variable first. So I'm going to take P minus 2 over negative P squared plus 4. But remember, I don't like negative leading coefficients, so I need to factor out a negative 1. That leaves me with negative 1 times P squared minus 4. Now, my numerator is fully factored. My denominator has a negative 1 pulled out of it. But I've got P squared minus 4. What is this? Well, this is a difference of squares, right? This is from section 5.3. If you need to go back and review, that's a 3. So this is going to factor to P plus 2 times P minus 2. If I foiled this back out, I'd get P squared minus 2P plus 2P. Those terms would cancel, and then a negative 4. Well, now I can see I've got a factor of P minus 2. That's going to cancel out, leaving with a 1 in my numerator. And then I have a negative P plus 2. And we could go ahead and distribute that back out if we'd like. They are equivalent. So I have 1 times over negative P minus 2.